Thank you very much for your kind introduction. As you can see from the rather lengthy title, we are talking basically on light elements, determination and quantification by TXRF in a special mode of excitation, namely having the chance to use for the light elements, the lower energies emitted from the rhodium tube, which are the rhodium L lines, and for the rack reflex at the rhodium K line, which is perfectly suited for the excitation of all the rest above the light elements, and which is, of course, interesting. It is possible to show that even with an 8 micron beryllium window STD, we can do such measurements. I take also this chance to talk about these effects that I want a little bit to fight against this conventional opinion that light elements is nothing for X-ray fluorescence analysis. And I hope to convince you with the slides and the spectra which we were able to measure. So as usually, the team was working together, and it is the result of the experiments done by several people. Some of them are here listed. It is Josef Prost and Dragic Krstajic, who joined the group very recently. And I think I start with information for this group. I could maybe skip, but this is the famous slide designed by Sigi Palke, who also introduced the TXRF technique in very heavy in his company, the vacuum chemistry. And you see the biggest difference in conventional excitation. We go under certain angles on the surface. All the interaction processes, photo effect we like, but the scattering we are not like, because they are creating background. They are fully detected by the radiation hitting also the detector. In the case of TXRF, we fundamentally have the same equipment. We have the source, we have the sample and the detector. Only the angle of incidence on the sample is completely different. It is small. It is below the critical angle of X-ray total reflection. This results in several advantages, which we will immediately discuss. You see basically that the primary beam is totally reflected, and the fluorescence which goes to the detector is very strong because of another effect, but the scatter is drastically reduced by the following effect. We have here the result. You have here the same sample measured in conventional system with a tracker system. You can see ppm levels very, very good. You have here the calcium, you have the standard selenium, and the rest is completely covered by the background. If you are looking on the TXRF measurement with the same sample, you see the background is very, very low, and you see all these elements which are in the ppb range or microgram per liter range, and the quantification is also given, and these numbers are the ppb levels from this standard, which is a certified reference material, this 1643C water. So why does it happen? As mentioned, we get the beam from the X-ray tube or other sources. We apply a very small angle below the critical angle. We excite the sample, and you see that this reflected beam is directed again through the sample. So we have something which is excellent. We have a doubling of the fluorescence signal as the excitation takes place by primary and reflected beam. Due to the total reflection effect, we have the primary photons in the reflected beam almost 90–95%. So only the rest of about 5% is penetrating into the substrate and thus result in a very, very low background because the primary radiation scarcely penetrates in the substrate. And something else which is of extreme importance and is a poorly technical advantage. The angles we are dealing are very small, about 1/10 of a degree. So we have a practically horizontal beam coming in and out, and we can come with the detector very, very close to the surface. And this is enlarging the solid angle of detection. So with these advantages, which you all know, we have here some theoretical curves. The reflectivity below the critical angle, in this case, it is a molybdenum on characteristic radiation on a quartz. It is about 1/10 of a degree. And you see that in the range below, you have a very, very high reflectivity and almost no penetration. This is what this results in a very low background. Above the critical angle, we have the opposite. Reflectivity is practically zero and transmission is full. The other one is now showing you the critical angle independent on the energy of the incident radiation. And as a material constant, you see here under the square root, the density of the material. So if we are looking on the same material, but with photons from, with one energy, but with different materials, we see that the critical angle is shifting. We have it here for the silicon, and the light gray one on top is the carbon. This is carbon and silicon, almost the same shape. And then the other materials like germanium, niobium, and tantalum. So you see, as the tantalum has the highest density, it has the highest critical angle, and the reflectivity curves are looking like this. This is for some interesting experiments when you want to increase the critical angle to allow still working in total reflection geometry. As for instance, with the germanium, you get a little bit higher angle of incident, which is allowed. And this gives a little bit more photons. But anyway, this is theory. The next one is showing you what are the difficulties due to limitation factors for the light elements. We have a low fluorescence yield. We have a air absorption of low energy photons. We have in general a low photo absorption coefficient, because this is depending on the energy between excitation and absorption edge of the element, and the thickness of the detector window, which is the real critical point. How can we improve? We have to perform the analysis in vacuum, so you get the air absorption out of the system, and then we have to use thin windows, either the thinnest available on the market, this is 8 micron beryllium, or ultra thin polymer windows, which are mounted on the detectors. And we will also show some results of the use of such a detector. The next is, this is the important part also of this talk, use an excitation energy as close to the absorption edge of your sample. And this is, for instance, in the next, you see the theory in terms of mathematical description. We have here what we want, a high incident intensity of the beam, then a tau k, which is high. This is dependent on the energy, as you know. So as close, as I said, to the edge of the element, this is fine. Then omega is generally low for the light elements, and the detector efficiency here we can only operate a little bit with special windows. And of course, solid angle is always an important influence to the intensity we measure. So you see here this product I0E times tau of energy dependence. Best is synchrotron radiation. Disadvantage, difficult to have access. So we go back to laboratory. We can use several materials for excitation of the light elements. And we, in this talk, point our focus to a low power anode, low power X-ray tube with a rhodium anode. And we are using the K energy at 20 and the L energies at 2.7 keV for the excitation. How it's done, we show later. So it was mentioned already, it is difficult, it is challenging, and these excitation sources must be carefully chosen. We are showing the last line with the 8 micron window and some experiments done with an ultra-thin window just for a comparison result. That is what I told you on the choice of the excitation energy. This is the run of the photoelectric cross-section for sodium 11 from 1 to 10 keV. You see, if you go with a chromium tube, which we use in reality, we have a very low cross-section. If you go here to the range of 2.7 for this rhodium L, we have already by nature an improvement almost of a factor of 100. So this is really great. So the lower the sample you want to excite is, that lower the energy of your sources. But the source energies are limited by the, basically by the absorption in the window. So how can we proceed? We have here a photo of such an ultra-thin window. It is supported by a silicon grid, and the thin layer you don't see, obviously, is a polymer which lies around. Thin means 300 nanometer. It is working, it is relatively stable, and we have here the transmission of such a relatively old one. We have now modern types, but you see something. With the beryllium window, we are in the range of about 40% in the sodium region. We have really almost the double transmission if you go to the polymers, and this is, of course, ideally and suited. But handling the ultra-thin windows is not so easy because they are light sensitive, they are really easy to break, and so I guess people are happy if they hear, I want to analyze sodium, I can do it with a beryllium. So this is how the detector looks, and this is what I was talking. Working is quite difficult. Nevertheless, we have another story to tell. You need in front of the ultra-thin window a magnetic trap, and this is costly because it goes on the distance from the sample. And the detector is light sensitive. You have to work, of course, in the chamber, but you have to cover really all light coming in through some windows. This is the detector we were working. It has this 8 micron beryllium window, an excellent energy resolution, and a 17 square active area. So with this, we had the setup and the efficiency, as I said already, we are in the sodium region here in this around 40% of the detector efficiency. Now we're coming to the chamber where the measurements in principle were done. I will show you two chambers. This is our old vacuum chamber without sample changer, and at the end I show you the one with sample changer, and the setup in fact is the same. We have the X-ray source, fine focus tube, high power, low power. We have a multi-layer for monochromatization to the anode material, if it is a moly, if it is a chromium, a copper, or a rhodium. So you have some multi-layers in use. And then you go in total deflection condition to the sample and place your detector as close as possible. You can watch the beam and control it by CCD camera. And what is also nice, the vacuum needs not to be high vacuum. It is rough vacuum, 1 millibar, 2 millibar is enough. And you achieve that with an oil-free membrane pump. So this is the setup, and we are going to have some photos. So this is the high-power tube. Here is the holder for the multi-layer. Here is the setup for the holder of the reflector, and this is where the detector comes into the vacuum through the feeds through. And this is high-power tube. This is the attached low-power tube, and you see this is relatively simple to exchange. Next is, why is low power so effective? Low power, of course, suffers that you are not getting 3 kilowatts, because the available power, as you have an air-cooled tube, is 50 watt, 35 watts. But you will be surprised how good is the output, for a very simple reason. As this tube operates in reverse voltage, so the high voltage is on the cathode and the anode is on ground. So you have the possibility to have here a very, very thin beryllium. It is can range from 75 to 125. And if you go to the high power tubes, they all have 300 micron thickness. And this is basically absorbing, for instance, the L lines of moly or rhodium to go through that window. So the focal size is quite nice. We have roughly 100 micrometer square, which we can put nicely with a slit to go on to the multi-layer, and then further on, as you saw it in the chamber sketch. So the samples we were using were multi-element samples. Sometimes lifetimes was 1,000 seconds, sometimes less, and then we extrapolated to get results. What I show here is a measurement on 3 different excitation modes. And you see the copper tube is a high power tube and excites relatively weak. It is the blue curve of the elements. If I go closer with my excitation, here we have 8 and here we have 5.4. You see already the drastic jump in intensity you achieve from the same sample just by the excitation, of course, due to the photoelectric effect. The green one is the low power tube with a special excitation that we don't see the real high energies, but basically the low energies. And you see the excitation is rather poor. Nevertheless, we see it. And we have a list of detection limits. We have for the sodium, chromium, 14, 25, and we were not able with the low power tube. And you see the rest is, as expected, is decreasing. So this means we are going to lower and lower detection limits. At least with this low power tube, we achieve 400 picograms for the titanium. Next is that what we have designed together, Christina Strengli and myself, and we call it Wobrauschek. You find our names a little bit behind. Wobi, that's me, STR is Strengli, and analysis with X-rays. So this system has exchangeable X-ray tubes, high power, low power, all what you want. Then a multi-layer and monochromatizer. And then what is convenient, if you have more samples, you have a tray where you can place 12 samples in line and analyze them one by one. So with this setup, we try to realize shortest distances from source to the sample and also from the detector, coming really very, very close. And we will show you some photos. This is one of the chambers which was distributed worldwide. You see here a high power tube. You see here the sample tray with the motors and the control units. Next is result done with this chamber and a chromium anode operated at 1500 watts. And you see really impressive. We reach about 1 nanogram detection limits. And if we say in picogram, you see 900, picogram 150, and 42 for aluminum, because it is closer. You see this high peak closer to the chromium peak. As usually all TXRF measurements, really fantastic low background, which is due to the monochromatic excitation and vacuum. So this was one setup, and we go now to another one, which was done with the rhodium tube, and you see the spectrum looks nice. And of course, we have already here some rhodium L lines, which are helpful to excite here, and therefore the sodium, magnesium, aluminium can be made visible. With this, we had with this tube, we are achieving now with a large detector, but the low power tube operating only 50 and 0.7. We are around 50 nanograms, 10 nanograms, 2 nanograms for these light elements. So this is showing you the disadvantage of low power in comparison to the high power. But anyway, you are in a reasonable range to detect. Next is we show some new approach where we have the multilayer as usually available in our beam path, but this multilayer acts as it is a fantastic polished mirror as well for both. It is creating, due to this lattice spacing, 2D, a Bragg reflex as a Bragg reflector. It is also being, because of its perfect flatness and high reflectivity, as a low energy filter, so letting the low energies passing, so we call it pass band. If we calculate the Bragg angle for the rhodium and the special multilayer designed for that, which is a palladium for the high set and the boron carbide for the low set layers, and a lattice spacing of 3.24, we get a Bragg angle according to the famous equation of 0.5 degrees. So this 0.5 degrees must be adjusted that you get the strong K line at 20 reflected. But as you will see now, you see the spectrum and you see the Bragg part, and this acts at this angle. But already visible is that at such an angle, we have a total reflection regime available, which lies at the angle which lies according to this angle. It starts to start here at around 5 and goes up to really about 90%. And this is the region we are using. So this is the secret of this dual excitation mode. So the dual excitation is extremely helpful when we are having the excitation of higher Z elements and lower Z elements. In addition, and this is really important, we can do something else. We can play around with the excitation voltage. If I go with the higher Z elements, I am going with 50 kilovolt to get a good excitation from the anode material, the rhodium. And if I only want more pronounced the L line, I go with a lower voltage, and we found out this 28 kilovolt is perfect to give a very strong rhodium L line, and also with a higher current to achieve this 35 watts we can do. So this is the range of the transmission energies, and the rhodium at 2.7 is about here. So very, very high. Yeah, here it is, 0.9. Okay, so you know now how we do the excitation. We know, we show you several of these developments of this chamber. The first was delivered to Jamaica through the International Atomic Energy Agency, one with these results, and these results for the chromium, which you saw. And this is one of the latest designs. It was delivered to the Baba Research Center in Mumbai, India, and it has not used this dual excitation from one, but we were giving them a chromium tube and a rhodium tube, which is exchanged and has the disadvantage that you have to realign the energy for the respective tube on the multilayer, which is also influencing the angle of incidence on the reflector. So this is one of the biggest advantages. If we go back to this excitation, you see that we keep the Bragg angle always at this position and have still two energies available. And with these two energies and the same angle, we do not need to change the angle of incident on our reflector. It's a real big, big advantage. So we go back where we were. So this is the setup. This side is our system, which we have since 2016 at our institute. So the same technical part, the sample changer, but here is the X-ray tube and the detector from top. And we can, of course, use several type of detectors, size, area, and window types. Okay, so else we have to make another, we had to make another advantage to use it optimally, this dual excitation. Namely, you see here that we have an air pass of 110 millimeters from the tube to the multilayer, and then the chamber window was here. And here is the reflector and the rest of the measurement unit. We were able to place here an evacuable tube with a window, and this is now the version which has an evacuable pass for the light elements, in particular for the rhodium L, which would be drastically absorbed on this total path length to the detector. So with this information, we are coming to the results. That is already what I said. We are operating 50 kilowatt and 28 kilovolts, and have, due to the different, to the 35 watts available, we can operate 50 and 0.7 milli and 28 and 1.4 milliamperes. And this change in the voltage and current gives us already a factor of 3. And here I'm again emphasizing no change of the angular setup for the total reflection part is necessary. So you see in the first slide, this is sodium with 28 excitation, and you see the result. We have short measurement. We get 147 counts, whereas with the high power, high voltage 50, we have 1/3. So this shows you the factor 3. It means we were then analyzing for calibration purposes multi-element samples these are the metals, these are the alkalines, and we were using our classical axial evaluation software package, where here in this row you see the data available for the intensities, which we use later on in our software to continue and evaluate it. Else, we have here the next as a result for given values using the axial with its own software, depending on the calibration due to the chemistry. So we see that the potassium and the calcium are having, well, we have here quite reasonable results for these levels. And when we use the fundamental parameter technique, which we are using in our developed software package, we see that we are really almost better. So it turns out that we have to do some more precise remeasurements on the calibration curves where we are using where we have to rely on the concentrations and the evaluation of the spectra. So the same is here achieved by the metals. So we see that the range is around 10% and better here, except of the lead, but I think there was a mistake in this measurement of the lead. Coming to the important results, what are the detection limits with our excitation for the light elements at 28? So we get for the setup of low power system 30 nanograms, 7 and 2 for the sodium, magnesium, aluminum, and for the higher Z elements, very convenient, we are already in somewhere 200 picograms. Of course, here the cesium value, these were the L lines measured, therefore we have not such good impressive data. Next slide shows the yes, yes, it's the same, just should not appear. Anyway, you see now some spectra of a multi-element sample. It is the standard reference material NIST. It is the 1643F, and you see that with the two excitation modes, we quite nice see the light elements, and here the rest of the heavy elements. And what is the matter? Oh, did I do? I have a little problem. No, I skip that. Okay, yeah, now. So, so these are the two excitation modes with another NIST sample, which we were using now for the complete evaluation. And here on the NIST, you see that we have a typical error at these PBB levels in the range 10 to 20%. And actually, we were quite happy. And with these results, I think we are close to the end. We were able to show that the light elements are able to detect from carbon upwards, but with special window detector. If you are happy from sodium upwards, you can use the 8-micron beryllium, and we have with our systems achievable detection limits in the nanogram. Of course, you can optimize it with a larger detector, with a high power tube, and with special detector windows as well. So I'm thanking you for your attention. and I hope you could convince you with these results. Thank you.
Thank you so much, Peter, for this highly interesting talk, and nice flowers here. And yeah, I think there will be a lot of questions, so the paper is open for questions.
Should I stop it?
Yeah.
Okay. Hello. See a lot of friends.
Yeah, there's a question from Ignacio.
Okay.
Hi, good morning. Very nice presentation.
Hi, Ignacio.
And yeah, I have in principle 2 questions. If you, first of all, probably I missed one slide, but if you have compared the results obtained with the chromium tube and the rhodium tube with double excitation, so in terms of detection limits and quality of the spectra, okay, the L lines of the rhodium has a lower energy, so they can excitate better than the low Z elements. And the second question is about carbon, oxygen, and nitrogen. So you deal with up to sodium. So, but in the spectra we can see also the other lines of the of lower Z elements.
So second question is easy to answer. When in the spectra where you saw the light elements, really carbon, oxygen, this was measured with the ultra-thin window detector, and I used it as it was there as a result to show the copper, chromium, and moly excitation, just to see, to demonstrate how drastically you are losing the intensity when you are far away from your with your excitation energy. The first question was again, what was the first question?
With the comparison between the chromium and the tube and the rhodium lines.
Well, the chromium, of course, you saw the drastic improvement in detection limits. We were around 1, and with the other we were around 40. So here it's the power. This was a high power tube operated at 30 kilovolts and 50 milliamps. So it is purely the flux which you increase. Still, we are happy due to the total reflection effect. Such high flux of photons coming are not increasing drastically the background. But this is TXRF, okay? But the photons are used to excite and therefore, of course, give you better conditions. So let me say maybe it is a general statement. If you have the technical possibilities like good water cooling, like high, of course, much more money because a high power generator is almost 6 times more expensive than the complete setup with the low power tube, because the generator is cheaper and the tube is cheaper. I think I have the numbers in mind. It's definitely a factor of 6 or 7.
Okay.
And then you must have the technical equipment. So and then of course you might go for the choice, go with high power and use these systems when you are able to get an X-ray tube on the high power basis with a thin window. I remember we had once a chromium tube, 2 kilowatt and 100 microns. It was 100 microns, I think. The problem was that after a relatively short time, normally, you know, such an X-ray tube lasts for years. And the problem when you're operating the X-ray tube in the classical mode with the anode grounded because of the water cooling, you have a lot of scattered electrons from the anode which are reaching the beryllium window from the inside. And they are really scratching away beryllium. And when you start with a thin window of 100 microns, you are destroying someday your vacuum because the window is not tight any longer.
Okay. Thank you.
Professor Wobrauschek, thank you very much for the nice talk. I have two questions. So one thing is basically, are you using any beam stop to stop the primary beam at the end of your sample?
The primary beam, in fact, goes in the camera, and the camera is on the aluminum, and there is some lead behind.
Okay. And since you're, yeah, one thing,
There are a lot of absorbers that
okay.
no primary radiation is passing out.
Okay. And what about, because you are using aluminum chamber, so
Yeah.
do you see any fluorescence or from aluminum, or are you using any any lining, acrylic lining?
No. Actually, we were really happy to see that neither the bending of the walls when you are evacuating is influencing the alignment, because normally people say, yes, we have to do it from stainless steel, the chamber. But we decided for aluminum for reasons for manufacturing it, and we use a trick. We are practically completely separating by an additional ground plate where we mount all technical components like multi-layer, etc., so that it is independent of the chamber walls. And this keeps us the stability of the geometry and of the mechanical components.
Okay.
So we had never problems with aluminum, and we had once a question in Stanford because they were all using stainless steel chambers, that the vacuum is a problem. It is not the case well, in particular, as I said, we have a rough vacuum, more or less.
Okay, rough vacuum, this is fine. And did you measure any time the background spectra without any sample?
From which samples?
No, and without any sample, just background spectra. Background spectrum without any sample, blank sample, with the blank samples.
No, not for aluminum. No, we never saw some blank. Our remaining blanks are practically from bed cleaning. We find a lot of iron in the, not a lot, but we find iron peaks, and no, we are so sensitive. We see really in some cases some picogram amounts, and this is the only thing which comes from our maybe not so perfect cleaning reagents and the chemistry of the cleaning. The reflectors are perfect. They are really super clean. The quartz reflectors, and also from flatness, it was a big advantage. So background goes down also for this reason.
Okay.
Of the surface quality of the reflectors.
Manoj was asking about spectra with sample support or without sample support.
No, I am just asking. I was asking.
No, without sample support, we have practically nothing, because in vacuum we have no.
If you don't have any support, you will not get anything. But with support, we get minimum background.
Yeah, as I said, coming from remaining dirt on the reflectors, and the rest is ideally it should be only silicon from the reflector and the scattered primary radiation. These are the two peaks which you have in your blank spectrum, nothing else.
Okay, good. So just why I was just want to ask whether you are getting any aluminum fluorescence from the background, from the chamber. But you say nothing. That is good.
But when you use synchrotron?
No, not synchrotron. Synchrotron means no. I am just asking, is there any background fluorescence of aluminum?
No, it was not coming. We have checked that the background from aluminum is not coming at all.
Okay, fine. Okay, good. That is what my worry. That is my question. It is good, very good. Nice discussion. Thank you.
Sir, myself, Kaushik, I have one question. Hello?
Yep.
Yeah.
Yeah. Sir, I am using that Wobrauschek instrument for last 7 years. And right now, while we are using chromium excitation, there is one problem that there is a huge background, maybe because of that electronic noise. So due to that background, we cannot able to go beyond fluorine. So if you are able to analyze carbon, you cannot see that peak because of that huge electronic noise. So is it because of that magnetic trap that is not working or anything? Is the reason?
No. The electrons which you are creating are three: photoelectron, Auger electrons, and Compton electrons. This is as a result of all the interactions. If you have your magnetic trap, you have a broad background in the low energy region, and you cannot measure anything because these electrons are penetrating through this ultra-thin window which you have on your detector and raise the background. So of course you can have a look if your magnets are still in good position or if they are slightly away from your collimator. But the background normally should be, as I showed in the slides, flat down to the carbon region in energies. So you could send me the spectrum and we could think. I mean, the detector is usually really sensitive to electronic noise which comes from outside, electric field, magnetic fields. We had recently this problem and we were solving it with ferrite rings around the important cables for the signal, basically, because these cables were well, they were catching unwanted signal from outside. And with our oscilloscope, I mean, it's really maybe a funny story. We could see the signals from the television station, which is in direct view to our institute.
Okay, so I will send you both both the spectra, that is initial spectra and right now whatever we are getting.
Yes, send me the comparison of the two, the situation, okay?
Okay, sir. Thank you, sir.
Hi, Peter.
Hi.
Very exciting results. Thank you very much for your presentation. I have two questions. Yes. Since you have a lot of experience with copper and chromium tube, just I wanted to ask you, is there any optimization in terms of the high voltage used? I mean, for example, using, for example, 28 or 30 kilovolt might be, or even 25 might be better for light element analysis instead of using 40 or 45 kilovolt, because you have a much lower high energy spectrum and still you have enough, let's say, over voltage to excite copper and chromium K lines. This is my first question.
Well, answer is very clear. You have a fundamental formula which says you the maximum of photon flux from the X-ray tube is about 3 times the edge energy. So in copper, let's say 10, so you would be already happy between 30 and 40, right? The chromium, we are always operating with 30 because the edge is at 6, so 30 is definitely enough to get a high flux for the chromium tube in all cases. So, and of course, in the rhodium, when we want the K lines perfectly excited, you go to 50. And then when we wanted this effect of getting this double excitation by the rhodium L, as where the multilayer acts as a passband, then it is much better to reduce the voltage.
Yes, this is
you are at 2 and increase the current.
Yes,
Now,
I totally agree. I totally agree. I mean, in terms of physics, we know what it is expected. What I wanted mostly from your experimental, let's say, tests and experience, if instead of having more flux, if operating the voltage, the tube at higher voltage, you have some scatter radiation which create, let's say, some more enhanced background around 2 kV because of the radiation that it is recorded by the silicon crystal and create some decomptonates. So from this point of view, I wanted just only to, if you have seen, let's say, some compensated effect in terms of
well, we have always in mind, on the one hand, we are monochromatizing for that reason, that we get rid of this high energy spectrum, which creates exactly this effect of the complex scatter in the crystal. So it is really important to have a really clean spectrum, monochromatic spectrum from the tube. And this is achieved by the slits, and else we have around the detector snout a collimator which does not allow any eventually scattered primary photons to enter from the side through the aluminum.
Yes.
So we have chosen silver as a very clean, pure material to form this snout shielding, this collimator, which of course has exactly the central hole according to the detector size.
Okay.
So if you go with 30 square, you make it 6 millimeters, and that is what you have. Else, we found out that this positioning of the detector close to the surface is really good when you have the shielded snout, and therefore the background conditions are so good.
Thank you very much. The other question is about quantification. With the last instrumentation equipment you have used with the double excitation, have you compared the light elements quantification, quantitative results when you have used 28 kilovolt with respect to the same results when you have used both excitation beams, I mean, with a high voltage, when you excite also rhodium K? Of course, obviously, it's much better when you use 28 kilovolt. I was just only wondering if you have seen any systematic, let's say, overestimation of the quantitative results when you have used both, when you have in your spectrum both exciting beams, the rhodium K and rhodium L.
Yeah, so you are completely right. When I'm operating with 50, I have 2 lines. The only story is that due to the restricted current I have, the L lines are also much weaker. So in total, the light elements having weaker fluorescence intensity, so they are not so strong. And this is resulting in already sometimes statistical problems because I'm operating 300, 400 counts for the sodium, which is not enough. Of course, I can compensate, not 1,000 seconds, go with 4,000 seconds. I mean, in special cases, it is rectified. Yeah, and if you have the instrumentation with the beryllium detector, okay, do it like this, and then you can use the complete calibration which you did for the 50, also including the light elements.
Okay.
I have to say, in the acceptable results were only achieved by the calibration which we got through Axel. When I'm going with fundamental parameters, which does the ATIQuant, I am completely wrong because I cannot properly or calculate the spectrum which is in this total reflection regime. It has this shape, from the reflectivity curve. So my potassium calcium is wrong. After the rhodium L line, so let us say the sulfur and these elements are becoming much better, but the rest is not so good. We have to work on that. We have some ideas to improve the situation by mathematical correction functions to the spectrum. But we are really intensively working on that.
Thanks, Peter.
Okay.
I have another question from Michael James Gattari.
Yeah.
Hi,
Good
Michael.
afternoon. Hi, Peter. Salam, many years, but that was a great presentation, man. It was a great presentation, and in many years. Anyway, it's a short one. I just wanted to know the lifetime of the tubes and the estimate of the cost of the new system.
Well, lifetime of the light low power tubes,
yes,
are for us. We have it for 3-4 years. Nothing happened. They are really good.
Okay.
So this is not a problem, because the power you apply is limited, as I said, 35 or 50, and we have air cooling. This is really working quite satisfactory. So lifetime, no problem. What was the other question?
The other question was the estimate of the cost, and probably if you are the volume, if you are to ship it, what is the kind of volume and weight you expect?
You are talking on the component of the tube or the complete system?
The complete system.
Well, this is depending on the designs you want, or the specialities you want. I mean, if you are interested, we can prepare a quotation for you. But I think you have the Bruker system. Haven't you got the Bruker system?
Yeah, we have a Bruker system.
Picofox,
the old one, yeah.
I mean, only the light elements are troublesome, but the rest is good.
That's what I'm saying.
Yeah.
Yeah, the rest is okay, but light element is a challenge.
Yeah, as I say, light elements are really challenging. Yeah.
Yeah. So anyway, you could send me a quotation, and then I have a look at it.
Okay.
And please let me know the weight.
Send me an email to make a reminder. Okay.
Otherwise, I have just one tiny question. So in one of the very first slide, you showed the femtosecond laser as an option for X-ray source. Can you comment on that?
Yeah. Well, we put that in a time when we were working together with the Vienna group on the femtosecond laser, and we found really out that the intensity you get in an extreme low energy range below 1 keV was fascinating. The real, well, even the spot size, because the laser can be focused very, very small, the spot size would also fit, but actually the main reason that it was not coming to an application is that we have not enough flux of photons there. But I know that there was a dramatic development on these laser plasma sources, giving us interesting energy range. And I think Birgit told me that she's very happy with this source, also in terms of flux and fluorescence results she gets. But we did not really take this into account. What we did, and we did excellent experiments, is the liquid metal jet. This liquid metal jet was, we visited them in Stockholm, and the Exilum group, and we got really, really excellent results. For simple reason, you have a really high flux from, or let's say high brilliance. You have such a small spot, you don't lose anything by your slit collimation system. And here with our multi-layer monochromatization. It was fantastic. But we had only the gallium, so you are limited in the energy with that. We have now in Vienna a gallium-indium source, and when it is operational, we will certainly do also some experiments on that. So, I mean, this is for me the most promising source aside of the synchrotron.
Yeah, exciting. Looking
Yes,
forward to the results.
Yeah. No, I mean, results really coming down in the lab in the femtogram range, I'm sure.
Impressive. There's another question from Abdallah Shaltut.
Ah, yeah, hello.
Will you turn on your mic?
He is off.
Okay.
Yes.
Ah, now.
Now.
Hello, Peter. Thank you very much for your nice talk.
Thank you.
And thank you for Osala for this invitation. My questions about the feasibility of direct solid sampling analysis using such suspension techniques with the TXRF, and what is the influence on the reflectivity in this case?
On the reflectivity,
I'm asking about the feasibility, about
stability. No,
feasibility, not stability.
It's really perfect.
I'm talking about the solid sampling analysis or the suspension analysis using TXRF.
We know the TXRF with the old X-ray tubes. They had some thermal expansion problems, so you needed to run it maybe 20 minutes. Okay, so with these low power tubes, the stability is really excellent. So we have no suspension. Now it was a misunderstanding. You want me to tell you what we can achieve when you have
suspension materials, yes, or solid sampling analysis, direct source sampling analysis with the TXRF. This is what I mean.
A lot of people are experimenting with this. I only say it is really very critical because of the particle size. You know, in light elements in particular. So light elements, your information depth is nanometers. So it is, for me, very critical. So a complete dissolution by chemical attacking Teflon bombs or whatever you are using to get it in liquid form transfer is possible. But
so what is the recommended particle size for to get reasonable quantitative analysis results?
I would say below micrometers, definitely. And then you have the real problem when you have your suspension, and this suspension is standing around. You have to get a, let us say, a procedure. How long do you shake? How long can you wait until this more or less homogeneous distribution inside your mix stays and you can take out pipettes? I think I was reading some months ago such a procedure description, and they said it is not more than 1 minute or 2 minutes when you have mixed it by a vortex mixer or so, and then pipette it on your sample carrier. So it needs, you could look in the literature. I don't have the citation now in my mind, but I saw it. They were reporting reliable results, but it is really critical. I prefer clear liquids.
Thank you. Thank you very much.
So, are there more questions? I don't see any more questions. I think we had a very good discussion. Thank you again, Peter. Thank you so much for the very nice talk and the vivid discussion that we had. And we have this applause thingy here under reactions. Okay. And I hope to see you all again on Friday, the 23rd of July at 4 p.m. Berlin time with the talk of Ignacio Allegretta. And wish you all a good day and good rest of the week, and be safe and see you again.
Thank you.
Bye-bye.
Bye-bye. Bye-bye.
Bye.
Thank
Have a
you.
nice day.
Bye.